Welcome to the how-to video for ionization energy. Ionization energy is how much energy is actually needed to remove an electron from the ground state of a gaseous atom or ion. So in this case, we could think about the first ionization energy. The first ionization energy just means we're removing the first electron. So if we're starting with a gaseous atom and we're removing an electron, we're going to form the sodium ion, Na+, plus we removed an electron. The second ionization energy means that we're removing a second electron. But that means that we've already removed the first, and so we really have the sodium ion that we're starting with. We're going to remove another electron, which means that we form the sodium 2+ ion. When we think of ionization energy, the greater the ionization energy, the more difficult it is to remove an electron, because it's how much energy is required to pull that electron away. The greater that number is, the less likely it's going to pull that electron away from that atom or ion. So when we really think about taking these electrons away, it really means that it requires more energy to remove each successive electron. So really the valence electrons are going to be the easiest ones to take away. And if we think of the periodic table and we were to just basically move across period 3, we'd go from sodium to magnesium to aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And as we go across the periodic table, we have more and more valence electrons available. So we can see the first electron from sodium that's being removed only requires 496 kilojoules per mole of energy. But when we go to take a second electron, it jumps almost tenfold. The reason for this is this first electron was in its valence shell, whereas this electron is actually in its core electron. That's going to be harder to pull that away. As you move over to group 2A, we know they have 2 valence electrons, and in that case, we'd see that first ionization energy is about 700. The second one's only a little bit more at 1450, but then the third one jumps up way, way more. Again, that's because as we remove those valence electrons and we get to the core electrons, such as in this third electron for magnesium, we now have this bigger jump. So really, when we think about the overall trend on the periodic table for ionization energy, we can really think about it's going to increase as we go from left to right across the periodic table. We increase in ionization energy. And same thing as we go up the periodic table. As you go up the periodic table, remember that you're getting closer and closer to the nucleus, and so those electrons are more and more attracted. Whereas if you're in the N=6 electron shell, you're really far away, and that electron is going to be a little bit easier to pull away. That concludes the how-to for ionization energy.